All right, so in this lecture, I want to talk about the power counting of NRQCD. We've kind of seen how we go about constructing a Lagrangian, but how is it that we actually know which terms we need to construct? So NRQCD power counting. OK, so how are we going to do this? Well, it's going to be like the other power counting theorems that we've talked about in the past in other parts of the course. So we're going to start out by adopting some notation to count the operators that are order v to a power. So we have to figure out how many operators do we have that are of order particular power of v. So if we say that we want to count operators that are of v to the power k, and have that scaling. And the number of operators, we can adopt an index for that, which is some integer. And I'll denote the integers with the following notation. Like our Lagrangian, we had these three different parts of the Lagrangian. We had the ultrasoft part, and then we had the potential part, and then we had the soft part. So I'll adopt the same type of notation for our indices here, where we divide up the indices into those different pieces. So once again, this is purely ultrasoft. This is greater than or equal to 1 soft. And this is the rest. And so I just look at my operators, and I enumerate them in that fashion. And this just counts how many are of order v to the k in this category, v to the k in that category, v to the k in that category. All right, so once we have that enumeration, then we can do the following. If we want to think about any graph in the theory, we can say the graph is going to be of order v to the delta, where delta gets contributions from different things. One of the things it gets contributions from is just the operators. So let's write a formula for delta. We sum over all the different k's. And each time we insert an operator, we get a k. And it doesn't matter what type that operator is. So we just add these indices up. But then there's other things that can give contributions to delta. In particular, there's some loops. And so there'll be some contributions from loops. And then it depends on what type of loops they are. If they're ultrasoft loops, they'll have a d4k that's going to give 8 powers of v. If they're potential loops, they'll have a d4k that'll give 5 powers of v. And if they're soft loops, they'll have a d4k that gives 4 powers of v. And then finally, there's some propagators in the theory. And the way that the propagators work is that they subtract some powers of v in the following fashion. So these i's are counting the propagators, and l's are counting the loops. So let me make a note of that. Loops, propagators. So the propagators are the propagators of the ultrasoft fields, potential fields, and soft fields. So why is it that they have the same integers here? Well, let me just show you, for example, where this -5 comes from as an example, and then you'll be able to see where the -4 and the -8 come from. So as an example, what's this -5? Well, you see, we already counted the fields in the operators here. So this -5 is a compensating factor because some of the fields are contracted into a propagator. So if we had a psi p dagger, which is contracted, then that got turned into a propagator that looks like e minus p squared over 2m. And the difference between the psi p's here, the power counting that we would associate to these would be that this is v cubed, whereas over here, this is a 1 over v squared, so v to the -2. And therefore, the difference is -5. And that's why we have -5 for each propagator of potential type like this. And similarly, if we went through the same logic for contracting ultrasoft fields or contracting soft fields, we'd get this -8 and this -4. So that's where those terms are coming from. OK, so we could just work with this theorem here, this formula. But it's kind of nasty because you have to count loops and propagators and vertices. There's a lot to keep track of. We can simplify it a lot by using what are called Euler identities. And the Euler identities here, there's more than one of them. So let me just first start with the one that's very natural, and that is that you sum over all the things in the field theory, all the vertices, subtracting the propagators, and adding the loops. And this is the usual Euler identity that sums to 1, kind of a connectedness. And then in the NRQCD, there's another Euler identity that comes about from the fact that if I erase the ultrasoft particles from the first identity, the diagrams are still connected. So that means I can simply sum over the potential in the soft, and I still have the same Euler identity. OK? So still connected, even after erasing the ultrasoft particles. And then finally, if I want to get one more identity, and that's what I'd like to do if I want to erase these, get rid of these loop and propagator factors. If I want to get one more identity, I'd like to erase, for example, the potential. So I could do that, and then I would just have Vs minus Is plus Ls. But it no longer has to be connected in this case. So now I can get a bunch of different disconnected components. And that means on the right-hand side, I can get some kind of integer, which I'm going to call ns. And that ns stands for exactly that, the number of disconnected soft components to the diagram. OK, so but that's 3 Euler identities. And we can use those 3 Euler identities to get rid of these factors here, exactly these factors. So there's some math to do that. And I'm not going to go through the math on the board. I'll leave the math for you to look at. But let me just tell you the answer of what you get for the power counting after you do that. So you get a formula for delta. I'm going to write it as delta minus 5. And then there's still a sum over k. And then I get the following combinations. I get k minus 8 for the ultrasoft. I get a k minus 5 for the potential. And then I get a k minus 4 for the soft. And those are all the terms in the sum over k. And then there's this integer ns, and that shows up as well. So the whole thing is minus ns. And that's the final power counting formula. And that's a very beautiful result. So let me put a box around it. So this result is very beautiful because it says, look, in order to do the power counting, all you have to do is count the operators and then know how many disconnected components you get if you erase everything but the soft fields. So this is a little tiny bit of topological information. And then it's just which operators do I build my diagram out of. And this power counting formula then tells you the answer. OK, so let's do a couple of examples of this. So one example that we'd like to do is the Coulomb. So in the Coulomb case, the way we wrote it is we had a alpha, and we had a momentum factor, k squared. And then we had some fields, psi dagger psi and chi dagger chi. And if we go through the power counting here, well, we've got in this prefactor, we've got a v to the minus 2. And then in these 4 fields, each of them v to the 3/2. That gives a v to the 6. So the product of these is v to the 4. And that v to the 4 means that this interaction is in the category V4P, because this is in the potential part of the theory. And then if I say, well, how does V4P enter my formula here? This is k equals 4. So it's k minus 5, 4 minus 5. So the way that this enters the power counting formula is it tells me that delta minus 5 is giving a contribution that's like 4 minus 5, which is minus 1. And that minus 1 is why we count the Coulomb as 1 over v, because that 1 over v is the minus 1. We often include the alpha that the Coulomb comes with, and that's the alpha over v that I talked about earlier, which we often take to be of order 1 when we're treating the non-relativistic system. Another example, which I can fit in over here, is the following. What if I took 2 Coulomb interactions like this? Now the power of the power counting formula in this form really comes to bear, because I don't have to think about the loop at all. I just have to think about how many interactions I inserted. And I inserted the Coulomb twice. And so this diagram scales like alpha over v squared. And so the bubble chain of diagrams that we do in the non-relativistic quantum mechanics, or the non-relativistic field theory, when alpha is of order v, is just dictated by the power counting. We have to consider the iterations of the Coulomb because those are all the same size. All right, so we've derived this power counting formula, and we've seen a couple of examples. And these examples we've done so far have just involved potentials. So what I'd like to continue with is do a couple of examples that involve both the ultrasoft fields and the soft fields. So let's start with the soft fields. And the type of diagram that we were drawing for the soft fields were these exchanges that were giving corrections to the potential that look like this, where these are soft. And so in this case, we look back at our soft Lagrangian, and we need to figure out the power counting of the vertices. Remember that the power counting formula only involves the operators and their power counting of those, therefore, of the operator insertions at these vertices, and not anything about the loop or the propagators. We've removed all that from our power counting formula. In this case, when we go back and look at the Lagrangian, the power counting for this vertex is a leading power interaction, so it's what we call V4S. And since there's two of them, we would say V4S is 2. And when we look at how that enters here, because we subtract 4, there's no contribution. So we're not getting any contribution from the terms in the square brackets here. The place that we're getting a contribution is from this NS, because in this particular diagram, NS is equal to 1. And therefore, the overall diagram is just scaling like a negative power of V. So we have delta minus 5 is minus 1 from that NS. And that means that if I count the alphas, that this graph, the overall scaling of it, well, there's 2 alphas from these vertices, so it's alpha squared over V. And that's why it's a correction to our Coulomb potential. So this type of correction is a correction to the potential that scales like 1 extra power of alpha, but the same power as V as the potential up here. And it's purely non-abelian or involves light quarks, as we have discussed already. So this type of correction is not a correction to the potential because we get an extra power of V. It's an iteration of the potential, and it makes it distinct from this one over here. OK, so that's an example of soft. We could also get things with higher powers of V, but this is sort of the first term that appears. Then the next example I'd like to do is one where we have ultrasoft fields. So let's do an example where we have a diagram involving ultrasoft fields. So we'll start with a Coulomb interaction, and then let's just dress it with ultrasoft fields. So here's an ultrasoft exchange. So we have 3 different operator insertions here. There's the Coulomb, and then there's the ultrasoft fields. And if we look back at our ultrasoft Lagrangian, it starts with something, or ultrasoft potential Lagrangian, where they couple together. It starts with something that has k equals 5. And the k equal 5 term, if we look at the interactions in that Lagrangian, it's really just the d0. So for k equals 5, it's just the A0 ultrasoft. And that actually, when we calculate those diagrams, it turns out that there's a cancellation for these diagrams. And the reason that they cancel is because there's a multipole expansion going on. And what the A0 gluon is doing is it's just measuring the overall charge of the system. So I have to add up all the attachments to the different lines in this diagram. And when I add them all up, there's going to be a cancellation. So let me write that. So the reason that they cancel is because due to the multipole expansion, they just measure the charge of the system, the total charge. So put the total in there. And the total charge of the QQ bar system is 0. So that's why these A0 gluons cancel. So the first thing that we need when we think about the scaling for the ultrasoft vertices is not k equals 5, but rather k equals 4. I mean k equals 6, the next term. And at k equals 6, we have interactions that had this form, which is what we call the dipole interaction with the ultrasoft field. So that's what the first non-trivial correction is, where we have a dipole interaction here. OK, so let's think about that. So that's k equals 6. So that's a V6. And then this is in the potential Lagrangian, because it's an interaction between potential and ultrasoft. And we have 2 of those. OK, so that's going to give a contribution here from this term. And then we also have the Coulomb interaction. So we also have a V4P, which is 1. And the V4P will also contribute. So when we add things up, we have delta minus 5, minus 1 from the V4P, and then plus 2 from the V6. I'm subtracting. I'm putting these in here and then subtracting the appropriate thing. So 6 minus 6 minus 5 is 1 times 2, and then 4 minus 5 is minus 1, so that's this minus 1. So overall, I get a plus 1. And that means that the scaling of this diagram is alpha squared v. There's an alpha in the Coulomb and then another alpha from the two ultrasofts. And then the overall scaling is v. So this is power suppressed relative to the Coulomb interactions. So this is a power suppressed term. And we don't need to include it until we go to higher orders. OK, so that's some examples of how these different terms in the action work. We didn't do an example that involved the ultrasoft Lagrangian, but that one only enters when we have a purely ultrasoft interaction. So that would enter, for example, if we did vacuum polarization on this ultrasoft gluon, and then the leading order interactions would just say that that's higher order in alpha, but the same order in V, for example, as a simple example of that.